Let's go. All right, let's get started. Actually, I might go back to the I'll go. All right, let's do a review. I don't have slides for this, but I'll solve some of the problems from the practice problems. But brief announcement. So you had homework to do on Friday, I would say, and we have posted the solution, hopefully. I saw the solution already, and Kayo and I worked out the solution. I don't know if it's up. Kayo should put it up. It's up? Okay. So that one is done. I would say homeworks 1 and 2 are probably very representative of the exam on Friday. Maybe like Tina said, the exam problems, because I'm trying a different thing right now. I think the exam problems are very representative of the homeworks. That is for sure. Maybe they're not super representative of the previous practice exams because of one thing. We split it into multiple questions because the way it's going to work out for the exam is we're not going to do it in class. You'll get, and we are still debating what the proper time is. I was saying 1 hour, but maybe we'll do it an hour and a half. So you'll get access to it throughout Wednesday, basically anytime on Wednesday. And then from the time you start, you'll get an hour or an hour and a half. I guess we'll decide with KU, Tina, and I what is plenty of time for you to work through the problems. And that's it. So then on Wednesday, we won't have a class, but I'll come here and then we'll do basically extra review session. So if you don't want to start the exam before the class on Wednesday, then don't do it. Then come here. You won't be able to pause it though. So once you start it, then you run with it. So I would say my recommendation is to show up to the class on Wednesday and then continue to ask me questions. And then we'll do like an office hours type of review session on Wednesday. And then after that, then you can take the exam anytime on Wednesday. And then, yeah, and then you'll get a shot at it. It's multiple questions. I think it's 5 or 6, 5. It's 5. 3 of them are more doing stuff and 2 of them are kind of theory questions. So should be fairly, I think the theory ones should be easy. And the reason why I wanted to have a couple of theory questions, I wanted to see what your conceptual understanding is. And because I know that I specifically was trying to trick ChatGPT to understand. And the other 3, you do have than, for example, the practice problems. Like this problem 1, there's no problem like this on the exam because this one you need to do the entire thing. So there's one question that is a subset of this, for example. Like this one has this A through F. There's no question in the exam that has all of these, but there might be a couple of things that you need to do here that you need to do in the exam. So there will be a couple of those. But you know, I can go through one of these. If you know how to solve this one, for example, I think you will be able to solve a couple of the exam questions. What was the other one? Is it just one problem? There's another. Yeah, there's another, obviously some strong form, weak form type of question. So you need to be able to know that. So I would say those 2, there's another one like this. So like these practice problems, I think are very much representative of the exam. Maybe there's nothing quite like exam, like problem 1. If you can solve this though, I think you are good. There's only a subset of this in the exam. I think that's about it for how it's gonna work out on Wednesday. Any questions before I get started? Yes.
Is it more like fill in the blank or?
No, you have to do some work and then you can either take a screenshot and upload the screenshot, or you can type it in the equation.
So we need to be able to upload our work.
Yeah, so in Brightspace, you can just take a screenshot and put it up. You can either type it in with the equation editor. So they are a little bit smaller. That's why I don't have anything like this, because this one would be so many lines of work that I didn't want to have something that would take pages. So most questions, like all 5 questions, they should not take more than a page each.
Okay.
So that, you can either type in what you need to type in, or you can take one photo and upload that. You can upload photos like JPEGs on. And the reason why I'm doing it on Brightspace is because there's a bank of questions so that people get basically a random exam. So there's question 1, which is certain style of question, but then there's several variations of that, and then you get randomly one of those. Very small variations like boundary conditions or numbers or the element, something like that. But so that there's basically some randomness and not everybody gets the same question. Other questions? Questions? All right, so let's get started. I'll do these 3 problems, and then we'll go from there. So this first problem, we have some 2 elements for this thing that is hanging from the ceiling, and then we basically have to write the mesh, then the element stiffness and assemble the global stiffness, the element body force and assemble the global body force vector, get the global system of equations and solve, and then plot the solution. All right, so we'll do everything. I'm already giving you what the stiffness matrix looks like. I'm already giving you what the shape functions look like. I already give you this. Wow, I give you everything. So easy. Let's do it. So the mesh, let's do the mesh first. Obviously you need the nodes and you need the X coordinate, right? So there's gonna be 3 nodes. And then what is my typical recommendation for making a mesh would be to number the nodes with the essential boundary conditions first and then the other ones. So here I would say the nodes, I would number like 0, 1, 2. So you can see that node, well, this is in Python notation, or you can do 1, 2, 3. So you can see that node 1 has essential boundary conditions, nodes 2 and 3 are free. And then for the elements, I would say this is element 1 and this is element 2. So node 1, X or Y coordinate, Y in this case, or X goes down. So this is 0, 0.51. And then elements, there's 2 elements. Element 1 is made out of nodes 1 and 2. Element 2 is made out of nodes 2 and 3. So that's my mesh. Then to assemble the global system of equations, the whole, yes. Really? I thought I was sharing my screen. Thank you. Good. Good that you're keeping an eye on that. Otherwise, I'm just talking. So yeah, so this is the mesh. I'll take this as an opportunity to tell you a little, when we solve this global system of equations, this is a little bit of a review of what the concept is. So how do we get the stiffness matrix and the force vectors? Remember that the stiffness matrix comes from this integral. We had sum over I, sum over J, Wi integral over the element of d n I dx with EA. So, and then d n J dx d omega E. Right, so if you remember, the stiffness matrix came from when we plugged in the discretization into the weak form, and then we rearrange it such that we take the sum and the Wi's and the Uj's out of the integral. Then this thing that was left here, this was the stiffness matrix of the element. And that definition was true regardless of what the shape functions looked like. So for the case of for linear elements, which is what we are doing here. For linear elements, there's only two shape functions, 2 nodes per element, 2 shape functions. So then the KE is a 2 by 2, right? Because the NI can take values 1 or 2. This NJ can take values 1 or 2. So therefore, in this case, is a 2 by 2 stiffness matrix. And it looks like this. So it's the integral for the element. So from x1 of the element to x2 of the element of EA, the derivative of the first function times the derivative of the first shape function. And then this so like that, but here this is N1 and 2. N2 and 1 is the same. And then last one is N2 and 2. Right, so all 4 combinations. And what are these N1 and the derivative N1 with respect to X? That one is just some number, you can work it out. I'm not gonna work out. Obviously, if this was quadratic, then it would look a little bit different. The N1 function will be some function of X, and then you can take the derivative and do the integral. For the case of the linear elements, if you plug in, I'll scroll up a little bit. I give you already, for example, here you have the shape functions and you can take the derivatives and you can take the derivative, put that into the integral, do the integral, and then you will see that this is just AE over the length of the element times the 1 minus 1 minus 1, 1. So at the end, I gave you already the stiffness matrix, so you don't really need to calculate it. This is for whatever the element, area, the element, Young's modulus, the element length. So in this case, you didn't even have to know all these details. I already gave it to you, but because this is a review, I can tell you that it comes from having put the sum of the nodal values times the shape functions into the weak form, taking out the nodal values out of the integral, and then just what is left in the integral is what defines that stiffness matrix. Yes.
So is it possible that an exam would get something that's nonlinear?
Could be. All right. So in this case, this is like that. For the force of the element, force vector of the element, I also give it to you, but where does the force vector come from? Again, here it comes from having, so putting the discretization into weak form, then you end up with sum over I, WIE, times the integral over the element of the B of X times the shape function. And this right here is that force vector. And so for this part, for the linear case, Ni can take either values 1 or 2. So for linear element, there's N1, there's N2. So the force vector can be, it's the same integral, it's just whether the shape function is 1 or 2. So the first entry is with N1, the second entry is same but with N2. So if this was quadratic, then you would need 3, right? So you have, it would look exactly the same, but you would have integral of B of X times N1, integral of B of X times N2, integral of B of X times N3. And here, for example, what does this integral look like? Well, it depends on what that B of X looks like. And this I mentioned in class. So if the B of X, there's ways in which this can simplify, right? So let me just say, so this one is the general case. If you have some B of X, then you would just have to do the integral. There's two cases in which I can simplify, and gave this in the notes. So simplify case A would be constant B. So where B of X is just a number, then the force vector is just the length over 2 times that value. So this would be B naught times the length of the element over 2. That is if the B of X is actually just some number. B of X equals just a constant B naught. The other one is if B of X is, for example, linear. Case B, B of X is linear. See problem statement. So if the B of X is linear, then I gave it on the problem statement. So if the B of X is linear, then the force vector, you just need to know the value of B at the beginning of the element and the value of B at the end of the element. This is the value of B of X at X1E, so at the beginning of the element, and the other one is the value of B of X at X2E, so at the end of the element. And then this assumes basically that B of X is linear. So those are two simplifications. The more general case is whatever the B of X is, you will need to multiply that B of X times the shape function and integrate. Right? So this is the more general definition of what the force vector is. The B of X function times each one of the shape functions, integrate, it will give you some value. Questions up to this point? Yes.
Could you be able to explain the length calculation again?
For this one, why is this the length?
And the one above.
The other one? The other one I don't want to do because it's too long, but this one is easy. So if it's just the constant, so for constant, that one I would say you don't need to know the derivation for the exam, but I'll just do it very quickly. So if it's constant, then you get this integral, right, from x1e to x2e of b of x, but it's just a constant, times the first shape function. And then this one is, again, from x1e to x2e, b naught and 2e of x. Now here, because it's constant, I can take that outside of the integral. And then I'm gonna be left with just integral of the first shape function and integral of the second shape function. You can plug in this function, you can plug that in and do the integral, and it will give you length over 2. But how do I know that it's length over 2 without even doing the integral? Well, because that function should go, the n1 goes from 1 to 0 from x1e to x2e, and the integral of n1, this is the only thing that I'm integrating, the integral of n1 is just the area under this curve. So what is the area of that triangle? Well, it's just the length times 1 over 2. So I don't even need to, you can just plug in whatever that function is. I mean, this one is, like I said, is right here. You can plug it in, you can do the integral, you can evaluate at the ends, but I guarantee you that the integral is nothing but calculating that area, which is just the length over 2. So for this one, that's how I know this is just length over 2. For the linear case, you would have to actually do the integral. That's why I don't want to do it, because for the linear case, then let's say that you want to integrate, b is linear. So then b is b1 times n1 e of x plus b2 times n2 e of x. This is how you can interpolate a linear function times n1. And then here it will be the same b. This is b as a linear function between nodes 1 and 2. So the same b, but times n2. Now, this I don't want to do because I cannot just use this argument of calculate the area. Here I would actually have to plug in this function, plug in the other function, and then I will get some quadratic polynomial, right? And then I will have to actually do the integral and do all the algebra, and I don't want to do that. But if you do it, it's the standard integral. You know, this one is some linear function of x, linear function of x, linear function of x. You will get some quadratic polynomial. Integrate that quadratic polynomial. The only thing that will appear in that quadratic polynomial are going to be b1 and b2, right? And then you integrate it, and then you will end up with, when you integrate it, you will end up with something that depends on b1 and b2. You can treat those as parameters, basically. And that's it. And so what you're left with is this expression. This reads, if you expand it, this is basically 1/3 LEB1 plus 1/6 LEB2. I'm just expanding it. And this one is 1/6 LEB1 plus 1/3 LEB2. But this comes out of doing this integral. I just don't want to do the integral, but it's just a quadratic polynomial, and then you integrate it, and then you evaluate at the ends at x1e and x2e, simplify a lot, and then you get that expression. But you don't need to do that for the exam. Know that expression. Like know this, you don't need to necessarily do that. Other questions? All right. Spending too much time explaining the theory. Actually, I haven't done the exercise, but let me just do the exercise, finish the exercise. So to actually get the global system of equations, I need to loop over elements. So for element 1, the stiffness matrix is going to be the area of that element, the Young's modulus of that element, the length of that element, times 1 minus 1 minus 1, 1. Then for element 2 is going to be the area of the second element, the Young's modulus of the second element, the length of the second element, 1 minus 1 minus 1, 1. And then also the force vector, let me do again. For the first element, the force vector is going to be, is this a linear case? I think this is a linear B. Let's see, actually it's a constant. You can see that B is a constant, right? Over each element. It's just the gravity times density times the first area, and then the gravity times density times the second area. So actually, I don't even need, in this case, I don't even need the full expression. I just need the constant approximation, so I can just do that. So this one will be the gravity times the density times area 1, and then length of element 1 over 2, length of element 1 over 2. And then for the second element, gravity rho A2, length of 2 over 2, length of 2 over 2. This looks like a 1. Should be 2. So that's the individual element stiffnesses and force vectors. And then I can actually put some numbers. Let's just put some numbers real quick. So what is A1? Let's see. A1 is just 2A. So it's going to be parameterized with A, which is 1. So just 2. So A1 is 2. And what is Young's modulus? 10 to the 6. And then the length is 0.5. Okay. So I just do it very quickly. So for the first element, A1 is 2, 10 to the 6 over 0.5. That's 4 10 to the 6. Times 1 minus 1 minus 1, 1. Yes.
For the F.
It is a 2, yeah.
In the matrices, are both of those L2?
Yes. Length of 2, yeah. Everything here is a very, very ugly 2, but it's a 2. All right, so K1 is 4 10 to the 6, 1 minus 1 minus 1, 1. K2, this is also supposed to be a 2. That one is everything the same, but the area is half. So this is going to be 2 10 to the 6. 1 minus 1 minus 1, 1. This one is rho, let's say 10. Because I don't want to do, rho, let's say 10, and then what was the other thing? Yeah, density 10 to the 4. Okay, so 1 10 to the 5th times 2. So 2 10 to the 5th, I think. Yeah, so this is going to be 2 times the length, which is, so okay, so this is going to be 10 to the 5th, 1 1. And this is going to be, I guess, 0.5, so half of that. Yes, 0.5 times 10 to the 5th, or 5 times 10 to the 4th. Hopefully I'm doing it correctly on the fly. So that is the individual stiffness matrix, the individual force vectors. Let's put that into the big K matrix and the big force vector. So this is the big K, the big force. For that, I need to use my mesh information. So this one is going to be 1, 2, 3, 1, 2, 3, 1, 2, 3. Element 1 is made out of nodes 1 and 2. Element 2 is made out of nodes 2 and 3. Element 1 is made out of nodes 1 and 2. This is made out of nodes 2 and 3. So I will add 4 times 10 to the 6 here, and then minus 4 times 10 to the 6, minus 4 times 10 to the 6, 4 times 10 to the 6, and then here 2 10 to the 6, so I'm gonna add here, so this is gonna end up being 6 10 to the 6, then minus 2 times 10 to the 6, minus 2 times 10 to the 6, 2 times 10 to the 6. 0, 0. And then for the force vector, I'm gonna get 10 to the 5, and then I'm gonna have 1.5 10 to the 5. And then I'm gonna have 0.5 10 to the 5. Just the standard assembly process. Yes?
Shouldn't the force vectors be half of what they are? A1 is 2, and then divided by 2 for length, and then times the length of a half. Should be 5 times 10 to the 5.
So this one, so A1 is 2, and then the length is half. So then A times the length is just 1, and then this is just 10, and this is 10 to the 4. So 1 10 to the 5, no?
Don't we also divide it by 2 on the length?
Oh, yeah, correct. All right, so this is 0.5, and so this is gonna be 10 to the 4. Good one. So this is 0.5 10 to the 5th. So you are correct that this one is gonna be 0.5 10 to the 5th. Then I should just do everything with 10 to the 4th. So this is 5 10 to the 4. And then 10 to the 4. Okay, so then I get 5 10 to the 4, and then 6. I feel like I'm doing something wrong. This one is definitely just 10 to the 4. And then so it should be 5 times 10 to the 4 and just 10 to the 4. There's something that is not quite correct. It should not be 5 times 10 to the 4. Because then it's 5 times bigger, which is not correct. So it was 0.25 times 10 to the 5th, right? So this one is actually, right, this one is actually 2.5 times 10 to the 4th. Oh no, yeah, it is 5 times 10 to the 4. Then the other one, how much is the other one? So 0.5 is 0.25. This one is 2.5 times 10 to the 4. There we go. Okay, that was the mistake. So this one is, like, it should be twice as much. Okay, now this is correct. Any other question about that one? Let me assemble and solve. Yes, Zach.
So on the exam, will we get partial credit if we make a mistake?
Yes.
Okay.
Yes, don't worry. All right, let me assemble the global system. So what does the global system look like? Again, the exam does not have a full program like this. This is way longer than what the exam will look like. But I still wanted to go over because, and yes, you will get partial credit. So this is the K times the U. So U1, U2, U3 equals the force vector from the body force. And then here we need to add boundary conditions, right? So the force vector from the body force is just whatever I just calculated. So this one is this. And then boundary conditions. That's what I'm missing. So boundary conditions, there is the node 1 has an essential boundary condition. So I actually know this value, but I don't know the reaction. So I should get a reaction here that I don't know. Then the middle node just doesn't have any external forces. And then the last node has a force, which is the other boundary condition. So let me scroll up a little bit just to know what the boundary condition is. So this one, you can see that there is an additional force here of 10 to the 4 over A. A is 1, so it's just 10 to the 4, right? So we need that extra 10 to the 4. So I'll go down here, and then I have this 10 to the 4. This is from that T traction times area, which is just 10 to the 4 over area times area. This is 10 to the 4 over area times area. So it's just 10 to the 4. Questions? And then to solve this, clearly you cannot solve directly because there's that reaction 1, which is unknown there. So you can, the usual way, you can either split this into 2 systems of equations. As usual, I don't really care how you solve it, and this is true also in the exam, which is why I'm not really asking that. But I don't care. I mean, once you set up this, how do you solve that system of equations? You can replace the first equation with the trivial equation. You can do the matrix partitioning that I've done before, where you basically split the rows according to the number of essential boundary conditions, and then you solve the subsystem of equations. So you have either replace equation 1 with trivial equation, or do subsystem of equation with matrix partitioning. How you do it, and then you can ask Python to do it. That one you can ask ChatGPT if you want. Once you get to that point, you can say, ask ChatGPT to help you solve that system of equations. That I don't care. I mean, because it's just, if you can set up the system of equations, how you solve it, up to you. Yes.
So if we're on the exam and we get to this point, do we have to show our work for solving this matrix?
No, you can say, I asked ChatGPT how to solve that matrix. I'll take that. And you just tell me, you want ChatGPT said U1 is this, U1 is, U2 is this, U3 is this, I'll take that. If you show me that system of equations and you say, I ask whoever, and then I solve that system of equations, and this is the result. U1, U2, U3 is that.
So all you care about that matrix equation at the top?
Yes,
and the final answer.
exactly, yes. So I do care how you get to that system of equations. I do care about that, because that is basically whether or not you understand how to assemble the system of equations. Then I don't care how you solve a system of equations. And then you solve the system of equations, good. Then you got some results. Yes.
So what was the boundary condition for
Node 3, yeah, so that one is the nodes have either a known displacement or a known force. So in this case, if you go back to the schematic, you can see that this first node is attached to the wall. So I know that that node has a known displacement. And the other node is not attached to anything, but I have this traction. This T stands for traction. And the traction is in units of stress. So it's in units of force by area. So you need to multiply by the area to get the force. Yes, it's just an applied force. Yeah, that's it. So the two boundary conditions is either you know the displacement, in which case there's an unknown reaction, which is why I put that R1, or there's a traction, and then it's equivalent to a force. Just multiply by the area, you get the force. Sounds good. So that's problem 1. I don't know the final answer, but whatever comes out of solving that system of equations. Other questions? You had a question.
Okay, so you keep mentioning ChatGPT. What resources are we letting you send?
Everything. I mean, you except each other. So you can look at your notes. It's open book. I mean, I'm not gonna be there, so you can take a look at your notes. You can ask ChatGPT. Yeah. So basically, that just don't ask other people. Not actual intelligence, not artificial intelligence, but actual intelligence. So no consulting with anybody. You are on your own. So knowledge resources like Python, ChatGPT, your notes, all of that is good. Definitely not allowed to ask anybody.
Yeah. So the later there's a certain plot. Do we have to do that in MATLAB or Python?
No, I don't think I asked for any plot in the exam. I don't think I asked for any plot in the exam. As if I were to ask for any plot in the exam, you can either just sketch it. The exam won't have any programming. If you want to do like for this system of equations, if you want to do it by hand, you can do it by hand. If you want to do it with Python, you can do it by Python. So I don't think I asked for any specific programming. Other questions? All right. So let's move on. I still get a chance to finish this one, the second one, and then I don't think I'll have a chance to do the third one. We can do that on Wednesday. All right, so this one, consider the strong form with boundary conditions, state the weak form, and what are the advantages of formulating the problem in the weak form. There are two main reasons. I can say both of them. All right, so strong form to weak form, you just did that for homework 2, multiply by weight function and integrate. So multiply, so x du dx squared plus x squared multiplied by w of x, integrate over omega. You can say from 0 to 2 or just say omega, it doesn't matter. Then integration by parts only on the second order term. So integration by parts only on the second order term. So I'm gonna, before doing integration by parts, actually, let me split it into x w of x du dx squared, and then the other term x squared w of x, right? So I still haven't done integration by parts. Just reshuffle a little bit so that it's clear that for the integration by parts, basically this is the second order term, and this is, so if you think of this as dB and this as A, then all we are gonna do is pass one of those derivatives to the xw of x. So what we're gonna end up is gonna be minus the integral from 0 to 2 of the derivative of xw of x times du dx plus the integral over the boundary, which is xw of x du dx at x equals 0, x equals 2. So that's the integral over the boundary. And the other term, we don't do anything to the other term. So just x squared w of x. Can we simplify this a little bit? Oh, and this is equal to 0. Can we simplify this a little bit? Yes, we can a little bit. So this will be either w of x plus x dw dx du. Everything multiplies du dx. And then simplify that. And then for the other simplification is use essential boundary condition here. So here for this term right here, what we know is that whenever we have essential boundary conditions, the W should vanish. So in this case, we have essential boundary condition here. So this is essential boundary condition. This other one is natural boundary condition. So we know that the W at 0 should vanish, and we know the derivative at x equals 2 is minus 3. So what we are gonna do is here, the term with the x equals 0 is gonna go away. So W at 0 equals 0. And on the other hand, we know du dx at x equals 2 equals, did I say minus 3? What was the, yeah, minus 3. So here I'm gonna end up with just minus x equals 2 times the minus 3 w at 2. So here, using du dx at x equals 2 equals minus 3 and w of 0 equals 0. So use boundary conditions on that term, and then finally write the weak form. So the weak form is find u of x. Yes. Minus 3. Oh, sorry. This should just be plus 2. Yes. Okay, so find u of x in C0 or H1. And this is just for continuity. So it has to be continuous with u of 0. So you have to state the essential boundary condition such that this is true. Let me just do this minus 6, such that this is true for all w of x in C0 with w at 0 equals 0. So this is the weak form. Questions? questions? All right, so this is about it for today. I cannot have office hours neither today after class or Wednesday after class because we have this faculty seminar. But KU should post on Brightspace to have office hours. And Wednesday, I'll be here. There's no class because it's technically the exam time. So what I'll do on Wednesday is I'll come to the class time and I'll solve the last problem and I'll answer questions. And like I said, for the exam, basically you have, if you don't want to come on Wednesday, you don't have to come. You have all day, and then from the moment you start, you'll get either an hour or an hour and a half, depends on if I get committed. I was thinking an hour, but your TAs wanted to give you an hour and a half. So
Let's go. Tito.
so you might get an hour and a half if I can be convinced.